So that was quite the introduction. But so now let's take a look at the language itself. What did these designers come up with? And first of all, remember we've been talking about these formal proofs and type systems, and JavaScript is a bad type system and all of these things. Well, these language designers of WebAssembly, are some smart people, and they knew about this. So, first of all, they defined WebAssembly. They had full semantics, operational semantics, formally defined, and also a type system. So, I'm not going to go into detail in this lecture, so that would be more something for formal systems, I guess, if you take this course. But what I want you to take away is that this language is completely formally defined in a mathematical way. And that means there are certain proofs that you can make about WebAssembly program. And that means you can provide some mathematical guarantees about WebAssembly programs. Or at least you can provide guarantees about abstract WebAssembly programs. That's not saying, and this is a big warning, that's not saying that executing WebAssembly by definition is going to be, for example, secure, whatever secure means. When you prove something about the model of his language, that's not the same as actually executing this language on a real life machine. Stuff can always go wrong. But you have a big basis of avoiding mistakes here, purely based in math. So this is a very cool thing. Definitely, if you're interested in formal languages, definitely check out the specifications of WebAssembly. There's also proofs about the type system in there. Definitely check this out. Now then, let's look at an actual program, finally, in WebAssembly. And here it is. You might recognize this nice bracket syntax. I think you've probably seen this if it hasn't changed in the previous years. You've probably seen this type of syntax this year a lot with CPL. And here we are again. WebAssembly works with these types of expressions, with the brackets. So what we see here is a module being defined. And then we have a function. Function add. And this function add takes two parameters, A and B, and both have the type i32. This is all just syntax. This function has a result type, is also i32. Now i32 stands for 32-bit signed integer. Sorry, this stands for a 32-bit integer. Not specified whether or not this is signed. So, then we have this instruction here, get local A. So right here, get local A. What that does is it finds the first parameter, get local B finds the second parameter, and i32 add adds these two together. But you might wonder, what a strange way of writing this like this, right? These are the arguments to i32 add. Why is it written like this? And I'm going to explain. WebAssembly is executed on a stack machine. So what do I mean by that? WebAssembly is an assembly language, a machine language. So machine languages are supposed to be executed by machines directly. So obviously this is not a language that your machine speaks. This is a language of an abstract machine. And this abstract machine is a stack machine. It works based on stack operations. And let me now just show you this by example. Without trying to explain it, it will become clear if I show you an example. So first of all, this function. This will consume two values from a stack. That's called a call stack. And it will replace these two values with one value. That's what the signature of this function says it will happen. So this function adds two numbers together, and this consumes 2 values, replaces that with 1 value. So what's going to happen if I call the function add? Well, let me show you. Let's call this function. If you want to call this function, you have to have a stack size of minimal 2 elements. And this is in fact a very cool thing. If you write a program, WebAssembly will know in advance. You can run a type checker over your program, and by the type system you can know whether or not you are allowed to call a function, whether or not it's possible, or you're always guaranteed when you call a function and this is allowed by your compiler or your verifier, that there are enough elements on the stack. So before I could call, you always start, for example, from an empty stack machine. And before it's possible to call a function add, you would have to call functions that grow the stack first. And so you can reason and make proofs about WebAssembly programs, and WebAssembly, or the verifier, will verify that you will never consume more elements from the stack than there are on the stack. You can never read more and not on the stack. It's a very strong type system. That's why we have these stack machines here. So what happens here? You have to have a minimum of 2 elements on the stack before you can call the addition function. Then when you call the addition function, immediately 2 elements are popped from the stack. And they are saved somewhere in a local execution context. And so when you execute get local A, then you push this parameter A back to the stack. Get local B pushes the parameter B back to the stack. Now we call the i32 add function, machine code instruction. And so the function that I've written here, simply a very simple wrapper. It doesn't do much more than what i32 add does. And what i32 add does is it takes 2 integers from the stack and replaces that with 1 integer. So this is a machine code instruction. And it replaces that with a sum. So if I execute this instruction, in one go, these 2 will be combined together and put on the stack, replaced by 15. You cannot call i32 add with less than 2 values on the stack, just like you can't call the function add. So this is what happens with our stack. And after calling this function, our stack size reduced by 1. So before we call this function, we need to first call some functions that increase our stack size, and then we can start decreasing it again. And the fact that every function has to define in its signature what it will do to the stack size, you can know in advance by looking at the signature what the effect of that function will be on the size of the stack. That's the entire basis of this type system, and that's one of the reasons strong proofs can be made. And so you can make guarantees about the stack size. You cannot write a program that infinitely increases this stack size. You cannot write a program that in the end will read more values from the stack than there are on the stack. So you cannot write a WebAssembly program. There is a WebAssembly verifier that will verify a WebAssembly program. So you cannot write a valid WebAssembly program that will read more values from the stack than there are on the stack. That's the power of this kind of stack machine. This is not the only approach to reach security. In fact, WebAssembly, the initial designs weren't even a stack machine, but this is eventually what they came up with. Let's quickly look at a different format here. So I've written this function, every machine instruction on one line. Now you can also write this with the bracket notation, and these 2 syntaxes are exactly the same. So you could have written i32 add, and then since it takes 2 arguments, you could do the function call just like this. So these 2 programs are just equivalent. For the purposes of explaining, I found the first one to be a little bit more clear. But so when you're going to write in the exercise session some basic WebAssembly programs, you can choose whichever syntax you want to use. These are equivalent. So let's look at the following WebAssembly function. We simply modified our original add function, and we added here another add instruction. Now, if you're going to try to run this, any WebAssembly verifier will tell you this is not a correct WebAssembly function. Why not? Well, let's take a look at this function body here. And let's first take a look at error message. Type mismatch. In i32.add, they expected i32, but they got just one i32. What does that mean? What does this message mean? Well, one of the nice things about WebAssembly is that you can verify a function independently. So remember, whenever you call a WebAssembly function, all of the parameters are instantly popped from the stack. That means it's possible to call this function with 2 elements on the stack. It's not going to be possible with 1. That also means, in the worst case scenario, for example, our stack is going to be empty, right? It's very possible to call this function from an empty stack. And in fact, WebAssembly, a function is not allowed to pop more values from the stack than there are parameters. So, what does this imply? This implies that you can verify this function body as a separate WebAssembly program starting from an empty stack. And then you can look at the end state of the stack and see if that corresponds to your result. So let's take a look at this function. So either WebAssembly function produces a result or it doesn't produce one, right? So let's take a look here. You start from an empty stack. Get local A pushes one element to the stack. Get local B pushes another element. We have 2 elements on the stack. i32 add needs 2 elements. It consumes 2 elements. And it produces 1. So after this instruction we have 1 element on the stack. And then we come to the i32 add. And then we come to what we see here. This is our type system basically. Our function at this point, our stack. This could be the type of our stack elements. Our stack elements have the type i32. No, this is the stack elements. We have the type i32. 1 element. Not 2 elements. And i32 add needs 2. So this function simply cannot be compiled. This is an incorrect function. So we're being protected from making mistakes. If we weren't protected here, we would pop a value from the stack belonging to something different. Not specified in our parameter list, which would be a bad thing. You cannot pop more functions from the stack. So if you want to pop functions from the stack as a you can write a function that netto removes values from the stack, but they have to be specified as parameters. So whenever you call the function, elements are removed from the stack and moved to the local execution context, right? But the body of the function itself, you can verify this starting from an empty stack. Now let's take a look at some more just syntax, things you can do in the WebAssembly language. So we're going to go more deep into all of this in the exercises themselves. Just wanted to give a quick introduction. You can call a different function using the call instruction. So this function here, add1, what this does is it consumes 1 value from the stack whenever it's called. And then it produces another value on the stack at the end of the function. So the end of this function ends with 1 result on the stack. And so netto add1 does not have an effect on the stack size. Consumes 1, produces 1. If you look at the body of the function, first pushes the local variable a to the stack. Then, so you start from the empty stack, you push a to the stack. Sorry, my mouse right here. Then you push the constant 1 to the stack. And then you call add, which removes both of these values from the stack and replaces it by a plus 1. So this adds 1 to your parameter. So you start from the empty stack, you end up with a stack with 1 element. That's your function body. That corresponds to your result type 1 element. So your function is correct. Now this add function, we of course had to check that we have 2 elements before we call this add function, but we do have 2 elements because we just pushed 2 elements. So you could even prove the fact that we have 2 elements here, right? So you can prove the fact that we can call add here. So we are allowed to call add here, which is the function we discussed earlier. So this is just an example of a function call. And you can only do this function call. I couldn't have done this function call a line earlier because my stack of my local function was not big enough yet. Let's look at something different. Branching. So this function is a function that checks if something is first parameter is greater than the second parameter. If the first parameter is greater, then we return 1. If not, we return 0. So function consumes 2 elements from the stack, produces 1. So first, when we call the function, 2 elements are deleted. And again, we start from the empty stack here. Now, this if syntax is a little bit special. You would expect the if condition to come right behind the if, but this is not true. First, you need to specify what each of the branches of the if are going to do to your stack. Basically, these are 2 separate, call it functions that are going to be called. Either the if branch will execute or the else branch will execute. Both of them need to have the same effect on the stack. If the if branch produces a value to the stack, the else branch has to produce a value too. And so that's what's being specified here. This if function, both branches have to produce one result value of type i32 on the stack. That's the type of this if function. This if function or this if statement has a sort of a type. And then let's look at the implementation. Then we first get the condition. So this is the greater than machine instruction, which compares these two. And then if this is true, we take the then. If this is false, we take the else branch. And these are our 2 branches. And since we said both need to produce one value on the stack, that's exactly what we do in these branches. So this first branch, the then branch, produces the constant 1. The else branch produces the constant 0 on the stack. So you could verify this if statement on its own. You know that what needs to be done, one value is being produced. Now in the context of our function, we know this if function will produce one value. So if that's all we execute, we start from 0, we add one value, we adhere to our result type. I hope you're starting to get an intuition now of WebAssembly, what the stack machine does, and maybe also the strict rules, why they can lead to more secure programs.